I'm from the Applied University of Bielefeld. I'm working in the OpenModelica world. I'm developing the backend. And yeah, on a very similar topic, we are trying to make the causalization process completely independent of array sizes, just as the talk before us, but with quite a different approach. Okay, I will give you a short introduction, then I will talk about resizable arrays and how to use them. And then I will talk about how I optimize these values to actually achieve the array size independent causalization process. And then I will show you some results from tests I made and a short summary. Okay, so state-of-the-art, as said many times, is scalarizing everything and blowing up the model in proportion. There's many different approaches to avoid this. And the approach we chose for OpenModelica is the pseudo-array causalization process. I presented this last Modelica conference, but to sum it up, the idea is to have everything that's symbolic stay in the array world. So differentiation and optimization processes, everything stays in the array world. The only thing that is still scalar is the underlying bipartite graph and directed graph to solve causalization, sorting and matching. So this is a very good idea in the sense of streamlining the processes, because we can use state-of-the-art or like the oftentimes mentioned matching and sorting algorithms. We don't need to change them in any way. We can just use the scalar ones. So, but the problem is that we still have the scalarized graphs, which scale obviously with size. So how do we avoid this? With resizable arrays. Resizable arrays, first of all, have some restrictions, but if we want to have an efficient array-independent causalization, we could take all the resizable arrays and resize them to the smallest possible size for our backend processes. And in that way, it will be independent of these sizes. The current implementation has some restrictions, as I stated here. I don't want to go too deep into detail. It's mostly an implementation-wise restriction. The most restrictive thing, I would say, is the connect equation restriction, because you would need to solve a certain connect algorithm from a connection graph. And to have that resizable requires more research. But the other things, we have solutions for. I won't go too deep into detail, just stated for this current restrictions. So there's a flag to activate that every array steering parameter is considered resizable, the resizable arrays flag. But there's also a OpenModelica resizable annotation to make individual parameters resizable. This is quite similar to the Daimler flag, but other than different to that flag, we put it on the parameter steering sizes instead of the arrays which are being resized. I will go into detail why that is. I hope we get to a standard, of course, here. There's a debug flag if you want to use it. So all of this is in the master, but proof of concept, of course, there is still work to do. Okay, task at hand seems easy. Find all resizable parameters, find their occurrences in the model, and scale them down such that the model becomes as small as possible. That sounds easy, but I will show you some small examples on why that isn't that easy. So first example, we have a parameter, a variable x with the size p, which is a parameter, which is supposed to be resizable. Then we have a for loop, which uses this parameter. One would think, okay, the smallest possible size, p0, not really possible because we need to have at least one instance in our scalar graph of this equation such that it gets sorted properly, and then we can resize it up. So in this case, first obstacle size is minimally 1, not 0. But then we could have a certain assignment at some point, and to assure that this for loop occurs in the model, now we would have to have an optimum of p equals 2 for the minimal size. Now this looks like quite the artificial problem, but I can assure you there is models that use parameters and add them up to have certain array sizes. So the problem here is this steers the array, the model size in a positive way. This steers the array size in a negative way. So we want to maximize P1 and minimize P2. And this actually is not one single solution. The optimum is for every P1 equals P2. So there's not one single solution. There's many solutions to this. Then there is the problem when the same variable influences one size positively and one size negatively. You would have to see, okay, what is the bigger factor here? And in this case, the optimal solution for P would be to be 499. You can't do this smaller. There's also just hard constraints on parameters. If you access X with the index 100, then it has to be at least of 100. Otherwise, your model just wouldn't work. All of this, what I'm telling you now, is not only a constraint on the backend resizing part, it's also a constraint on simulation. You would, if you have resizable parameters, you would need to stop the user from actually putting P lower than 100. Otherwise, this model just doesn't work. So all of this analysis is also good for simulation, to have proper error messages for your, for the simulation. Okay. Now I showed you a lot of different obstacles. How do we combine all this to a proper problem that we can solve? Well, it's an optimization problem. Specification of it sounds dire. In general, it's an integer valued nonlinear optimization problem, which is in general NP hard. But we have a lot of freedom, actually, because most of the time it will be linear, most of the time it will be convex. And for the solution, we also don't have a big quality. We don't need the best quality. We just need any optimal solution that is reasonably good, that is feasible. What do I mean by that? If the algorithm converges to n equals 1,000 for any n, for any input n, basically, then it's already shown what I want to show, that it's independent of the original array size. Even if it's a big constant, it's independent of the original array size. So we had two approaches, but my point is it's about the optimization problem, to formulate that properly. The solution, finding the solution isn't as hard. We used a simple hill climbing algorithm with two different approaches, starting at a reasonably good point, using min-max values that are defined and trying to reach feasibility, or the other way around, starting at a feasible point, using default bindings and trying to reach optimality. So, but it's not about solving the problem, it's about defining it. So what's the main advantage? As I said, it's beneficial to scale it down so everything is independent of array sizes. We want to have a target function that optimizes these parameter values such that it minimizes the size of the equation system. And we have to define several constraints to our optimization problem. First, some structural variable constraints. That could be box constraints of any form to variables, min-max values, these sort of things. Structural equation constraints, implied array size equalities. If you define the left and the right side of an array equation, these sizes obviously have to add up. So this could tie several parameters together in size. And we have to retain the equation structure. This is basically every equation has to exist. None is allowed to stop appearing in the scalar graph. Okay. In mathematical terms, this is our target function. We want to minimize f of x for x, where this is just a function that depends on x and symbolizes the size of one dimension. If you multiply all dimensions of one equation, you get the size of the equation. Then if you sum up all equations, you get the size of your model. Okay, what our constraints, variable constraints, as I said, user-defined box constraints or subscript implied constraints. I already explained that if you access a certain variable at 100, it has to be at least of size 100. So we look at the subscripts of x, and this has to be less or equal to the dimension defining expression. In our case, it was just a parameter. Then we have these equation size constraints. The left-hand side and right-hand side for each equation has to be of the same size. And equation iterator constraints. These are the constraints that ensure that every equation exists at least once, such that each iterator iterates over at least one value. That's what this equation does. Okay, so I talked about the problem. I will show you a model for which we applied this. We had an insulated rod model from Martin Otter that I think you made it for another paper, but you gave it in the...
It was as a benchmark for the open scaling project.
Yeah, a benchmark for the open scaling project. There's 3 different versions of it. There were different solutions for this, but we took the most natural approach, the equation approach, where all the dynamics are in equation form, which is the most natural way how you would go about modeling. It looks like this. I want to just highlight the main parts of this. There is the parameter integer nt, which steers array sizes. This one is now supposed to be resizable. Then we have 2 variables that are steered by this array size, and we have which we obviously want to minimize. Then, we have these 2 equations. These already have some implied constraints, namely nt has to be greater than 1. This is this constraint here because it's accessed as 1. So the dimension of t has to be at least 1. And nt has to be greater than nt because of this. These are obviously trivial constraints, but I just want to showcase on how to actually gather these. Then we have the next set of equations, which has similar implications. We have this size is nt plus 1, and it's accessed as 1, so nt plus 1 has to be at least 1. And this one, nt plus 1, has to be at least nt plus 1. Trivially as well, but gathered nonetheless. Then, last but not least, we have 4 equations in our system. These also have implied constraints. Each of these has to have at least 1 element. So this will be converted to nt minus 1 because nt has to be nt minus 2 because nt has to be at least 2 for this to exist. For this, nt has to be at least 1. And also from these 2, we get our target function, which is 2 times nt minus 1, which essentially is just the size of this, which is nt minus 1, plus the size of this, which is nt, and then we get to this target function. If we combine everything, this is our whole model. We could throw away a lot of constraints, and this is the only constraint remaining that actually constrains our problem. And we can easily see, global optimum is 2, independent of what nt you originally put in here. So easy enough for this model. You could assume that there's models which have a lot more convoluted, but this is one just for the sake of simplicity. So I want to show you now how the improvements look. This is the old version in the back end. How on the bottom you see the number of equations times 10 to the power 5. And on the left you see the time in seconds it took to simulate. The old backend actually had some problems, so this, not simulate, just build the model to target code. This actually had problems in the old backend just because of size issues, and it didn't actually come to simulation. So we developed a new backend. This already looked better. There's an improvement. We also could just simulate more models, but the problem is it's still scaled the same because as I already explained, we still solve the underlying scalar problem. So it doesn't matter how much we strip from the rest, there's still one part scaling in the same way. And now with this resizable approach, we can see that there's no scaling at all. I mean, it's trivial but impressive. So I wanted to show it really doesn't scale at all. And you could theoretically put this on any array sizing, any array steering parameter that for the time being doesn't break the rules I mentioned at the start. Okay, quick summary.
Okay.
So what did we recently do? We found the structural analysis and optimization such that it scales of 1. The code size also scales of 1. And we also achieved the simulation time reduction because this leads to more optimal code. I don't want to go into detail here, but in the old version, we had integer lists for what the for loops had to iterate. Here we just have straight up ranges. So the code size strings and the lookup time for simulation also shrank. So what is the current improvements that are needed to make this better? We need a code generation of O1. This is an OpenModelica problem. And we need to actually have error resizing after compilation. Right now, we only use this for the backend process. But as Modia does, we also, of course, want to have it actually resizable in the target code. So this is ongoing work. There's some more steps we need to take to have that possible. And last but not least, the real improvements will be simple connect equation resizability. We have ongoing work with Exergy and with Francesco Casella for certain industry-grade models to actually apply this resizability. And for that, we need simple connect equation support such that it can handle those. Last thing is split equation resizability. Don't want to go too deep into detail, but in the matching process, you could have a result that a full for loop cannot be solved in the same way. That half of it has to be solved for some variable on the right-hand side, half of it for some variable on the left-hand side, and so you need to split it up. That is something we also work on. We have a basic solution, which would be just solve it implicitly, but we try to come up with something more sophisticated such that the target code stays efficient. Okay, thank you for your